Okay, so good morning or good afternoon. Now, this video, hopefully it will make sense, but I just, I'm a little bit incapacitated, so I can't, yeah, I'm not functioning optimally. However, now this course, we've had disadvantages. So what I did is that these questions as I set up are more like a guide, as in you're able to answer all these questions, and you are covered more or less reasonably enough for us to sit an exam, all right? So far, I shared with you 4 pages of some work, which were basically answering this question here. Given the complete graph K4, compute all the eigenvalues of this graph. And that question also is related to this other one here. State the maximum eigenvalue, maximum degree theorem for a graph G. Hence, use K5 to exhibit the theorem. So anyway, now here, let me just go to those page one. Where is page one? Oh gosh, now I've opened the wrong pages. Sorry. Hopefully it will open. Okay. So page one is this one there. Now, the idea is, I don't know if they've done some graph theory, but here we are actually using linear algebra in graph theory. Now, graph theory just basically means a graph is just an object that consists of vertices and edges. Like here you can see vertices, they're just the points, and the connections, or what we call the edges or arcs, okay? And when you talk about a complete, well, so a graph can be, a simple vertex. When you think of a network, you're talking about a graph. So here now I'm trying to make a very short video, so let me just get to the point. So we'll say a graph is complete if every point is connected to every other point in the graph. For instance, you can see this one we're calling K4. We have 4 vertices, V1, V2, V3, V4, and you can see V1 is connected to V4, V3, and V2. V2 likewise is connected to everybody else, and so on. So you can represent it this way or this way. Likewise, you have K5, which is 5 vertices, and each vertex is connected to the other vertex. Okay. Now, there's something that I talk about later on, which call about degree of a vertex. So degree just means the number of edges or lines that come from it. In other words, its connection to others. That we also call it adjacency, and we form what we call an adjacency matrix. So, let me see page two. No, where is page two? Page two is here. So here now I have the adjacency matrices for K4, K5, which is basically what's going on is that if you look at K4, you can see if I'm talking about adjacency matrix means that it's going to be ones or zeros. Zero if there's no connection. So you can see V is not connected to itself, so you will have zero there. So this is V1, V1, V2, V2, V3, V3, V4, V4, these zeros. And then since every vertex, V1 is connected to other vertices, so you have 1, 1, 1, 1, 1, 1, 1 everywhere else. Same thing occurs for K5. So that's about it, as far as the adjacency matrix is concerned in this particular case. Now, we now bring in the aspect of eigenvalues, and you remember how we compute eigenvalues. We just talk about what we call a characteristic polynomial. Basically the determinant of the matrix we have, which we're calling A, minus lambda times the identity matrix. In our particular case, these are 4 by 4 for K4. So we have A, K4, which is this matrix, minus lambda times I4, 1, 0, 0, 0, multiplied by lambda. So you will end up with 0 minus lambda is minus lambda, then 1 minus 0, and so on like that. So you have minus 1, minus lambda, 1, 1, 1. 1 minus lambda, 1, 1. 1, 1 minus lambda, 1, 1, 1, 1 minus lambda. This is the characteristic polynomial whose determinant, now these two lines means determinant. And so if we find the determinant of this, we'll actually find the values of lambda, for which this is 0. So to determine the values of lambda, you can use row or column operations to reduce the matrix nicely, or you can apply some software. So here, I think, anyway, it's better to learn. I guess you do the hardcore mathematics. So here you use row or column operations to say what? That, we're given a matrix A, which is ABCD. The determinant of ABCD is the same as the negative determinant of if you exchange the rows with the columns. Column 1 becomes, no, row 1, which is AB becomes row 2, and row 2 becomes row 1. So the determinant becomes negative. If you exchange columns, the same thing occurs. If you, now, the determinant remains constant if you don't change. You can see now, if let's say I replace, in this case, what happened here is I fixed row 1, AB, but then I make the new row 2 to be row 2 plus row 1. So I have this. The determinant of this is the same as determinant of that. So that's basically what now I send you to look at and more or less follow the trend. Hopefully it would help. So now again, we have like 5 minutes from my video. I do want more than 10 minutes. So now the character, so to find the value of lambda for this particular case, what I did is the idea is to try to make zeros of these columns or rows to simplify our matrix. So we apply row or column operations to obtain determinant easily. So what I did is I fix column 1. This one you fix it. And then now you change the others so that column 2 is column 2 minus column 1. Column 3 is column 3 minus column 1. Column 4 is column 4 minus column 1. If you perform that, you can see the first column is the same. Second column will be 1 minus lambda is 1 plus lambda. Then minus lambda minus 1 is this. And then 0, 0. And the others, the same thing occurs. Okay? And then so you can see that now we have introduced zeros in the matrix, meaning that it's easy to get the determinant. So now the next thing, I use the rows so that I did row 1 is row 1, row 2 is row 2, row 3 is row 3. So fix row 1, row 2, row 3. And you only change row 4. So you just say row 4 is row 4 plus row 1. What happens is that the first 3 are the same. Then you have 1 minus lambda, then 1 plus lambda, then 1 plus lambda, and then 0. Now this last column is 0, 0, 0, except this part. So now we can find the determinant. So determinant becomes, now using signs, so you have 1 plus lambda times a cofactor of 1 plus lambda. Now, this is in negative position, so you have minus 1 plus lambda. The cofactor of this is just to delete the rows and the column where they are, so you will remain with this matrix, which is 1, 1, 1 minus lambda, minus 1 plus lambda, 0, 1 plus lambda, then 0, minus 1 plus lambda, 1 plus lambda. This is a new matrix we have. Next, we do the same thing, something similar. Here, what I did, I don't remember what I did. What did I do? I kind of fix the first row and then and the second row, and then the third row I just added the second one. So you have this plus this is 2 minus lambda, then 1 plus lambda, and then 0. And then you have 0, 0. So now next you have minus 1 plus lambda times this guy. So you get minus minus. So 1 plus lambda squared, cofactor of minus lambda, this one. You delete this, the row and the column where it is, you end up with 1 plus lambda. Hopefully you can see, by the way. Zooming in. I hope it makes sense. Right, so you end up with this matrix. And now the lastly, you just add this to this one. You get 3 minus lambda, 0. And then now you find the determinant. So it turns out that this is the last part you have. So determinant of this is just this times this minus this, which will give you minus 1 plus lambda cubed, 3 minus lambda, which you set to 0. So you end up with lambda 1 is 3, lambda 2, lambda 3, lambda 4 is minus 1. So there we have the eigenvalues for that. So K4 is said to be 3 regular. And anyway, I can say many more things, but that's, at least for now, I want to stop there. So at least I have something to have, talked about. So let me see, how do I stop this?